Welcome to lesson 6.1 on discrete random variables. Count the number of siblings in your family, including yourself. Be sure to include all of your stepbrothers, stepsisters, half-brothers, half-sisters, and all those living, and only in those living now. Let x be the number of siblings. So x can be something from 1, meaning that there's only one of you, all the way up to maybe 9 of you. What are the possible outcomes for x? We filled them in here, and fill in the table as a class. So one year I had these siblings inked in, and then I added my 2019 students to it just to get a little bit more numbers. So I then had 30 students total, okay, combining the 2 years. So here there's 1 student, here there's 16 students, there's 6 students, 2, 2, 2, and 1. The probability of a randomly selected student having more than 9 siblings is so small that we call it negligible. A random variable takes numerical values that describe the outcomes of some chance process. Random variables example. The number of pets owned. You can have 0 pets, 1, 2, 3, 4, and many pets. The number of cars sold at a dealership. How many cars were sold today or sold this month? And that can be a random variable taking on something from like 10 to maybe 200. The number of baskets made by a basketball team's point guard. The amount of money earned by a U.S. citizen. What is a probability distribution? A probability distribution of a random variable gives its possible values and their probabilities. It can be in a table or a histogram. Same definition as in the previous chapter. What and how often? So how many siblings continued? Make a probability distribution of the siblings table from above. Here we have up to 7 siblings that we actually that someone actually had, and then the probability. So 0.03, 0.53, 0.2, 0.0000. Okay, what is a discrete random variable? Give some examples. It has a fixed set of values. So a discrete random variable could be something like 1 to 7, where there's not infinite number of possibilities, like 1.1 and 1.001 and 1.0001, and we can't get in between values of siblings. They're just whole values in this case. It has gaps between, like 1, 2, okay. Oftentimes these are things you can count, like the counting numbers, 1, 2, 3, 4, okay. In most applications, x takes on a finite number of possible values. The same ideas implemented with more advanced mathematics apply to random variables with an infinite but still countable collection of values. Examples of discrete random variables are shoe size, where you have 9, 9.5, 10, 10.5. Even though we have half sizes, there's still space between, and there's these increment amounts. Okay? Non-example is a foot length, because you can technically measure a foot to very many decimal places. So we view that as more of a continuous random variable, where from 11 to 12, we have a whole continuum of sizes of foot length. Show that the probability distribution of x is a legitimate probability distribution. So therefore, all the probabilities are between 0 and 1, and all the probabilities add up to 1. That makes this a legitimate probability distribution. And I have all the probabilities being added up to 1. Make a histogram of the probability distribution and describe what you see. So for 1 and 2, 3, 4, 5, 6, I put in all the probabilities on the left-hand side here. And along here, I put number of siblings. Okay. The distribution of siblings, I should mention shape, and I should mention maybe like a little bit about center and spread and outliers. The distribution of siblings is skewed right. The skier would ski right. Is skewed right with a center at about 2 siblings, because that's about where my 50% mark is, because I have about 53% of families having 2 kids. Varying from 1 to 7 siblings, so a little bit about spread, without outliers or gaps. Outliers and gaps are mentioned. What is the probability of randomly selecting a student with at least 3 siblings? With more than 3 siblings. So probability of at least 3 is the probability that the random variable x is greater than or equal to 3 versus the probability of more than 3 siblings, which specifically means more, so only greater than 3, so the probabilities of 4, 5, and 6, and 7 siblings. But equal to 3 means 3 siblings, 4, 5, 6, 7 siblings. Okay, and I'm just taking the probabilities straight from the table before. 3, 4, 5, 6, and 7 siblings, or just 4, 5, 6, and 7 siblings. Okay. All right, so then we get 0.434 and 0.234. Okay, let's skip the next one here. All right, E. Given that a student speaks more than one language, what is the probability the student speaks 3 languages? Okay, so given the student speaks more than one language, what is the probability the student speaks 3 languages? So here is my more than one language. And so I'm going to use the cover-up method, and I'm going to say that that's my total then. Given they speak more than one language, what's the probability they speak 3? So probability that x equals 3, given that x is greater than or equal to 2, or that can read x is greater than 1. So that's a probability of A intersect B over probability of B. So the probability that the person speaks 3 languages and more than 2, well, that's implied, and over the probability of just more than 2. So we would take the goal amount, 0.065, and divide it by the sum of those 4. And that's equal to 0.176. One wager players can make in roulette is called a corner bet. To make this bet, a player places his chips in the intersection of 4 numbered squares on the roulette table. If one of these numbers comes up on the wheel and the player bet $1, the player gets his $1 back plus 8. Otherwise, the casino keeps the original $1 bet. If x equals a net gain from a single $1 corner bet, then the possible outcomes of x are to lose $1 or to have 8. Here is the probability distribution of x. Lose 1 or have 8. You lose 1 34 out of 38 outcomes, but you gain 8 on 4 out of 38 outcomes. If a player were to make his $1 bet over and over, what would be the player's average gain? Pretend the player plays exactly 38 times. So then out of the 38 games, they would probably lose $1 34 times, and they would gain $8 4 times. So we would have lose $1 34 times, and then gain $8 4 times. So 34 times they would lose $1, 4 times they would gain $1 out of 38. So they would lose $1 34 38ths, and they would gain $1 4 38ths. And that's an easier way to consider it. And what this is technically is each value of the random variable times its probability, and the other value of the random variable times its probability, and we're going to find the expected value, which means a value of the random variable, okay, and that's weighted by the fact that 34 38ths are the odds of -1, and only 4 38ths is the odds of gaining 8. So we would expect to lose 5.3 cents per game in the long run, and that's how a casino is making their money. If a player were to make $1 corner bets many, many times, very important, the average, okay, we're being technical here, this is the mean that we found, the expected value is an average, the average gain would be about, because we're not making any guarantees, we're not really expecting to lose 5 cents, okay, would be about a loss of 5 cents per bet. In other words, in the long run, the casino keeps about 5 cents for every dollar bet in the corner bet in the roulette. How would you calculate the mean or expected value of a discrete random variable is the formula on the formula sheet. Mu of capital X, of the random variable x, is equal to the capital E, which stands for x, expected value of x, which equals the summation of each xi times pi, which means each value of x times its probability. How do you interpret the mean or expected value of a discrete random variable? You need 2 things. how many repetitions or trials or draws or rolls or selections, and the word average. Oh, sorry, you need many, not how many. You need many repetitions or trials or draws or rolls or selections, whatever your context is, but you need many, and you need average, approximate, estimate, about, some of these words here. Okay, and then we did that right up there. Calculate and interpret the mean number of siblings, mean of the random variable of x. In the example on the previous page, use a histogram from earlier. Okay, that mean is the balance point. So one sibling had a probability of 0.03 of occurring. Two siblings had probability 0.533. Three siblings had probability of 0.2. And then I keep going. 4 times 0.067 plus 5 times 0.067 plus 6 times 0.067 plus 7 times 0.033. But I just put a dot because it's a notes packet and we get the idea. On a test, you would have to write them all out. Okay, equals 2.846. Now what does this mean? Do you have a 284% chance of doing something? No. We found that the random variable, the weighted average, meaning that we're accounting for it being half as likely to find a random AP Stats student that has 2 children in the family versus 1 versus 3 and so on. We found the weighted average to be 2.846 children per family. So on average, AP Stats students have about 2.846 siblings, including themselves. Okay, so what did I say? On average and about. Is 5.7167 a possible value for x? And explain, no. This is the idea of a discrete random variable. We don't have values like that for number of siblings in this context because we say that number of siblings is a constant. Someone cannot have that type of sibling count because number of siblings is a discrete random variable. Okay. Does the expected value of a random variable have to equal one of the possible values of the random variable? And should expected values be rounded? No, don't round your expected values. It's okay that you can't actually have 2.846 siblings, but this is the average number of siblings in my AP Stats class. So the expected value can be any value equal to or between the possible values of the random variable. Do not round the expected value of x, written in either notation form. Let y equal the number of times in minutes it takes a randomly selected student to run a mile. Is 5.7167 a possible value for y? And explain, yes, that many minutes is technically possible for a run time. Y is not a discrete random variable in that case. You have minutes and seconds and hundredths of seconds. Suppose that x is a discrete random variable with probability distribution to the right, and that mu x is the mean of x. Okay? Then the variance of x is variance x equals sigma x squared is each observation minus the mean squared times the probability of that observation, and the summation of all of that. So the summation of each observation minus the mean squared times the probability. So this way we're weighting it for the probabilities of each observation so that more likely observations are weighted greater and less likely observations are weighted less, and that we're finding the average distance, the average squared distance each value is from the mean value. So first we would really need to find that mean expected value. Then we can find a variance or a standard deviation by square rooting each value's distance from the mean squared. Okay, this is not on the formula sheet, but this is. That's the main reason that I bring this up, or one reason I bring this up is because you can then get standard deviation by square rooting the variance. How do you interpret the standard deviation of a discrete random variable? The number of blank that a typical blank has will typically vary from the mean mu x by about sigma x. It is the average distance the outcomes are from the mean. If you use your calculator to calculate and interpret the standard deviation of x in the siblings example. So before we found that the mean was 2.846, so I'm going to take each observation, like one sibling, and subtract it from the mean and square it and times it by its probability. So that means I'm taking 1 minus 2.846 squared times 0.033. Then 2 minus 2.846 squared times 0.533. And then each observation's difference from the mean squared times its probability. So after I do just a couple terms of it, I'm going to put a ... because this is kind of tedious. And in the end, my calculator tells me I get 1.458. The number of siblings that a randomly selected student has will typically vary from the mean number of siblings of 2.846 by about 1.458 siblings, and that's using this sentence. Okay. Standard deviation is used to measure risks for investments. If something varies a lot, then there's a little bit more risk because maybe it will gain a lot, but maybe there's a good chance that you lose out as well. So maybe that's better for long-term investments. Are there any dangers to be aware of when using the calculator to find the mean and standard deviation of a discrete random variable? You must show some work to get credit. If you just drop in an answer, 0 points, even if you interpret it well. The first couple of terms is fine. You must turn the frequency back to 1 after graphing a probability histogram so that your calculator can work on future questions. What is a continuous random variable? Give some examples. Now, this is a type of random variable that has no gaps between the possible x values. It's on a continuum. So again, shoe size versus foot length. Is it possible to have a shoe size of 8? Is it possible to have a foot length of 8? We say yes, you can have a shoe size of 8. No, because can you really have 0.800000 inches? It's very unlikely. So the probability of 8 itself is 0, okay, because it's 1 over infinite many options. How many possible foot lengths are there? How can we graph the distribution of foot lengths? There are infinite possibilities. A histogram with infinite number of really skinny bins that adds up to 1 or approaches a smooth density curve. How do we find the probabilities for a continuous random variable? Find an area under a density curve. For a continuous random variable x, how are these two related? They are exactly the same for a continuous random variable, okay, like one that we estimate with a normal curve or a smooth density curve of some other shape. Okay, so these two are exactly the same because of this discussion up here. The probability of exactly one number is 0. So the boundary line adds no area, the boundary of A itself. Another way to illustrate why continuous probability models assign probability of 0 to every individual outcome is to remember that each outcome is just one of an infinite number of possible outcomes, so the probability is 1 over infinity. Realize that there was a difference between these two things for discrete random variables, though. So let's jump back to the past, where we saw that I said like less than 3 siblings, right here. Greater than or equal to 3 siblings, or just greater than 3 siblings. One of these included 0.2, the probability of 3 siblings, 4, 5, 6, and 7 siblings, and this one only included 4, 5, 6, 7 siblings probabilities being added up. The weights of 3-year-old females closely follows a normal distribution with a mean of 30.7 pounds and a standard deviation of 3.6 pounds. Randomly choose one 3-year-old female and call her weight X. Find the probability that the randomly selected 3-year-old female weighs at least 30 pounds. Discuss why weight is continuous. Okay, so weight is one of these continuous random variables because we say that we're not exactly weighing just a pound or right on a pound, but that we could have decimal amounts of pounds, and so we just go on to say continuous. We also take normal to give us a hint that this is going to be considered a continuous random variable. Then we're going to be doing normal approximations. So the probability that x is greater than 30, now pause here. The only reason you can jump into using a random variable is because they defined it. If they didn't define it, then you would need to start with a phrase like that. Let x be a randomly chosen 3-year-old female's weight. Okay? Then you can jump to here. Probability x is greater than or equal to 30 equals a probability that z is greater than or equal to 30's z-score, which is a probability that z is greater than the 30's z-score is negative 0.19, just below this right here. Just a little bit of a standard deviation below here. And that's 0.577 that you would be above that value. So 30.7 is the mean, 30 is the value of question, and we're saying that that's about 58% of the area of the normal curve, which seems reasonable. Find the probability that a randomly selected 3-year-old female weighs between 25 and 35 pounds. 25 and 35 are not on standard deviation markers, so that means I have to use normal approximations. I can't use something like the empirical rule. So I'm going to say the probability that x is between 25 and 35 is 25 z-score and 35 z-score, which is negative 1.583, positive 1.194, and the probability z is between those is 0.8270. So remember, when you go from context to z's, you have to show work, but when you go from z's to area, there's no work. Someone very smart made tables and graphing calculators for us. So remember, this is how normal CDF works: lower, upper, mu, and sigma. If the probability of x is less than k is 0.8, find the value of k. Oh, I'm sorry, we don't do that one. Okay, thanks for watching.